In today's class, we will see how we can use Gauss law to find out electric field due to a uniformly charged infinite plane sheet. Using Gauss law, derive an expression. Using Gauss law, derive an expression for the electric field due to a uniformly charged infinite plane sheet. Using Gauss law, derive an expression for the electric field due to a uniformly charged infinite plane sheet. That is a question. So we need to find out the electric field due to uniformly charged infinite plane sheet using Gauss law. So first we will consider a large plane sheet. Let us consider a uniformly charged plane sheet. Let the sheet has surface charge density equal to sigma. We will say the surface charge density is equal to sigma. So let us say we need to find out electric field at some point P, which is at a distance r from it. So let us say electric field is to be obtained at point P. We need to find electric field intensity at point P, which is at a distance r from the sheet. So it is obvious that the Gaussian surface will be a cylinder. The Gaussian surface will be a cylinder of radius 2r and area A. Not radius, of length. A cylinder, the Gaussian surface will be a cylinder of cross-sectional area A and length 2r with its axis perpendicular to plane sheet of charge. So our Gaussian surface will be like this. So this is the plane sheet. So I'll write here. So this is uniformly charged plane sheet. and this cylinder is the Gaussian surface. So this is Gaussian surface. Cylindrical Gaussian surface. Cylindrical Gaussian surface. Now let us apply the Gauss law. So when we apply Gauss law, so we know that integration, surface integral of E into ds. Surface integral of E into ds is q by epsilon naught. Now this cylindrical Gaussian surface has three faces. This is the flat surface, this is also a flat surface, and this is the curved surface. So we'll consider a small area in each of these surfaces. So let us say this small area is delta S. So here area vector and electric field are parallel to each other. E and ds, or let me say this area vector A and the unit vector n. Similarly here also the electric field E and area vector A are parallel to each other. Now in this curved surface, so the electric field E and area vector are perpendicular to each other. You may consider this a small area ds also, ds, and this also ds, small area ds, and this also, because we are considering this, or because we have considered the whole area, you can write it as A also, no problem. A and here E and ds are perpendicular to each other. So total flux is E into ds, which is also equal to q by epsilon naught. So now this area is divided into three parts, that is integration of left plane surface, left plane surface, plane surface into E into ds cos 0 plus integration of curved surface, curved surface curved surface. So this is for curved surface, it is E into ds into cos 90 plus integration of right plane face, right plane face or plane surface, right plane face or surface. This is again E into ds into cos 0, which is equal to q by epsilon naught. So now cos 0 is 1, so this can be written as E into A. Integration of ds is total area A plus 0 plus E into area A equal to Q divided by epsilon naught. So 2EA. EA plus EA is 2EA. 2EA equal to Q divided by epsilon naught. Also, because sigma is the surface charge density, so also Q is equal to sigma into A. So substitute Q is sigma into A in this equation. So we get 2EA equal to 2EA equal to sigma into A divided by epsilon naught. Or simplify, you get electric field E is equal to A get cancel, sigma by 2 epsilon naught. So the electric field intensity due to an uniformly charged infinite plane sheet is given by sigma by 2 epsilon naught. So the direction of A is normal to plane sheet and directed away from sheet when the charge is positive, and towards it if it is negatively charged. So we can write here the direction. Directed normal to the surface of charge sheet. Directed normal to the plane sheet. Plane sheet. Away from it if it is positively charged. Away from it if it is positively charged, and towards it if it is negatively charged. If it is negatively charged, and towards it if it is negatively charged.